have the position function, we know that the velocity of that position will be the derivative of the position function, and the acceleration will be the derivative of the velocity, or the second derivative of the position function. So how that will look like in a vector definition with the polar coordinates. So we have the vector here. This is the vector that we are going to use, where x and y are defined by the trigonometric functions, right? As we have it here. So we have this magnitude, we have the angle, and we also have the unit vectors that are defined by this equation. This is the unit vector. Okay, unit vector is basically the same vector that we have extracting the value r, and the derivative of this vector will be the second vector that we have of the angle, right? We can rewrite our vector, which is r, right, I r of theta as r that multiply cosine theta I plus sine theta y, right? Which is the same thing to write r, right? So it's the same thing. So let's write it here. The summaries is okay. Now what? Now we need to do the let's get the velocity. The velocity will be the derivative of r, right? The velocity vector will be the derivative with respect to the time t of r, okay, which is the derivative of r multiplied by the unit vector r. This is a multiplication, so we need to do the multiplication rule, and this is the derivative of r with respect to t, and we keep this r as it is, plus r multiplied by the derivative of the vector, the unit vector r with respect to t, right? And what is this derivative of the unit vector? So let's look for it. The derivative of the unit vector r with respect to t is equal to the derivative with respect to t of cosine of theta I plus sine of theta y, right, which is equal to minus sine of theta, and theta is in another function, so we need to have the derivative of cosine plus multiplied by the derivative of theta. This is an inner function, plus cosine of theta multiplied by the derivative of theta with respect to t of y, right? This is I. So if I do the common factor here, I will have the derivative of theta with respect to t, that multiply sine, right, a plus cosine of j, or in other words, it is the derivative of theta with respect to t multiplied by the unit vector, this one. So let's write it here. The derivative of r with respect to t is equal to the derivative of theta t multiplied by this, right? Now, what is, just for curiosity, what is the derivative of the unit vector theta with respect to t? Basically, we have the same thing with respect to t, that multiply minus sine theta I, right, plus cosine theta j equals to minus cosine of theta, but because here we can do the factorization, the common factor of the derivative of theta also, same thing as we did there. I will, sorry, this is I. I will skip that steps. Theta j, right? I multiply by the derivative, which is the same. If we see, this is the same to this one with a negative, right? So this is minus the derivative of theta with respect to t of r, right? So let's write it here. The derivative of the unit vector theta is equal to minus the derivative of theta with respect to r. Okay. So the velocity will be equal to the derivative of r with respect to t of r, right, plus r derivative of theta t will be this one, okay? Because if we see here, this is the same r, but this one is this one, right? So we replace it and we have it there. And this one is the same. We didn't do anything there. We just got the derivative of r. Now what? Let's continue with the acceleration. Okay? Acceleration will be the derivative of the vector, the velocity vector with respect to t, which is the same. To do the derivative with respect to t of the derivative of r with respect to t, right, plus r the derivative of theta with respect to t of the unit vector theta. We have to include this. This is a multiplication, and this is another multiplication. This is another multiplication. So we have three multiplications there. Let's get one by one. So the first one is the double derivative of r with respect to t, right? That multiplied r, the unit vector r, plus the derivative of r with respect to t, that multiply the derivative of the unit vector r with respect to t, plus, so this part is only for this one, okay? Now let's go with this. The derivative of r with respect to t multiplied by the derivative of theta to t multiplied by this one, okay, plus the derivative of all of this. So we have r, right, that multiply the second derivative theta back to t, right, plus the derivative of this one. So we keep it this as it is, multiplied by the derivative of the unit vector. Right? Now, what can we do? We can reorganize this, and let's see what happens. Let's reorganize. So this one we keep it as it is. Let me just, all of this is only this part. Okay. The derivative r plus the derivative of r d, the derivative of theta dt, remember this, plus the derivative r dt, the derivative of theta dt of this one. So I'm bringing all this together, okay, plus, if I multiply this internally, r we keep it doing this, and multiply it by r. Okay. And then what can we do? And by the way, this is the same as t squared r. Okay. Finally, if we take the common factor of this one and the common factor of this, all these three, we will have right, which is this one, right, minus r I forgot to write this. This is minus. This is minus because we have it here that this is minus. We repeated this replacement. Okay. Minus r the squared, right? Plus the unique vector that multiply by 2 dr dt, the derivative of theta with respect of t, plus we have it, we have two of these, right? Plus r into theta dt. Okay, so we have two components of the acceleration vector. This is the component that is related to the magnitude. This is the of the unique vector, and this is the component that is reference to the angle with respect to the unique vector of the acceleration. So this is the acceleration. Okay.